everybody. Thank you for joining today's webinar. My name is Fran Porcel, Principal Application Engineer here at RTI. I'm very excited for this webinar. This is part of a two-part series. In the previous one, Om and I discussed at a more theoretical level how RTI's products and Medcrypt's products work together. But today I'm excited because we're going to show a live demo of all of that. I've been working in medtech in the last 4 years in the professional services team at RTI. What we do at RTI is my professional services team, we explain to our customers how the product is used. We help them debug it if they need to. We help architect the product around it. At the end of the day, we are advising them how to use the RTI product. Would you like to go ahead and introduce yourself?
Yeah. Hi everyone. My name is Om Mahida. I lead product management and Medcrypt. We spend well, I personally was also spent the better part of the past 8 years helping medtech companies, both medical device manufacturers and others, with cybersecurity and building products to solve their needs. Super excited to continue the conversation Fran and I had last time and get into a actual demo of using the tool and how easy it can be to secure your medical device. And then Eric, do you want to give a quick intro?
Yeah, thanks, Eric Pancoast here, CTO and co-founder of Medcrypt. I've been unofficially building Medcrypt since 2014 and officially starting in 2016. And I'm excited to dig into this. Back to you.
All right. Thank you, Om and Eric. Would you like to go through the agenda?
Yeah, just to really do a quick review of the agenda today, we're going to recap some of the topics we talked about last time around what challenges MedTech faces and around security and connected systems. We'll dive into a use case study that we're going to actually demo. Fran's going to demo with a live system running locally on his machine. Then talk about how Connect security extensions work at a high level, how Guardian works at a high level, and then go back into a demo of a secure system using both those technologies. And then we'll summarize the call with some key takeaways in the Q&A. Like Kate mentioned before, if you have any questions, feel free to use the Q&A functionality within Zoom to ask those questions, and we'll answer them during the Q&A at the end. So doing a recap of challenges in cybersecurity and for connected systems, right? Kind of the basis for a lot of this, outside of just the technology aspect, is that the regulatory landscape's been changing. In the past 2 decades, we've seen the FDA and other regulatory agencies start adding new guidances that are related to cybersecurity. And in the past couple of years, we've really seen a push through both pre-market and post-market guidances, as well as some new acts that gave regulatory agencies like the FDA more power to enforce these cybersecurity regulations. We're seeing this a lot in the US, right, North America market between the FDA and Canada Health, but also in EU through MDR and other regulatory agencies around the world. So the thing that's really changed in the past like 5-10 years is that you have regulatory agencies now when they're reviewing your medical device for clinical functionality and safety, they're also looking at the cybersecurity aspect of it. And this cybersecurity aspect, right, we kind of summarize it here, right, through like 5 key categories. But right, to actually execute this, it's a little bit more complicated. There's a lot to do with making sure the data you have, right, from both patient data or even control data is secure both in transit and at rest. You have things like authorization and other best cybersecurity practices around who's actually allowed to access data or view it, and then are also following best practices for updating your device over time. This is kind of just a high kind of requirements list of what cybersecurity and medtech means around some of these security controls. But right, we can definitely talk about this slide in more detail, and we did a little bit on the last webinar. But what we're going to talk about today is like how to do this, right, when you're actually implementing your system. And one of the more things that makes cybersecurity and medtech more difficult is when you have clinical systems like surgical robots, MRI machines, right, and others, well, you have this complex technology being deployed. You have all these different components, all these different subsystems needing to talk to each other, needing to have security requirements right outside of security of needing to be real time, where reliability is really critical, performance is really critical, right? You wouldn't want a vital sign getting to back to the UI where a clinician is looking at it, to be delayed, due to some performance issue, or a control of a robotic arm to be delayed or slightly off, right, even by a millimeter, due to some performance or other technology issue. So there's already hard technical requirements on making sure you have this complicated system be able to meet these requirements. And so when we add cybersecurity on top of that, it becomes, right, even more challenging of like, okay, how do we ensure we're meeting all these complex requirements around real-time data, high reliability, and good performance, while also making sure all this is secure.
Thank you all for that introduction and the recap of our previous webinar. We're going to focus the rest of the webinar today on this use case study. We can see here a diagram of pretty standard medtech device or set of devices. This diagram is actually coming from the RTI medtech reference architecture that you can find available online. If you just search for RTI medtech reference architecture on Google, you will find it. We have a GitHub repository, and this is actually part of the first demo of that reference architecture. As you can see here, we have an ARM controller. Imagine an application that is sending, or the surgeon is controlling this arm controller to send commands to a robotic arm. We have an orchestrator. Someone in the OR could be looking at a screen that is giving you information on how the system is behaving. Then we have a patient sensor that sends vital signs to this patient monitor that is just displaying those vital signs. And as you can see here, we have a number of topics. We have motor control, device status, device heartbeat, device commands, and we also have the vitals topic. You can see that some of these are publishers if the arrow is pointing towards the Connext data bus, or they can also be subscribers if the arrow is pointing away from the data bus. They're subscribing to that data. So we're going to show, as part of the demo, we're going to see these applications. We're going to see some of the data flows. And as part of the demo as well, we're going to see how an attacker is going to try and come into the data bus, connect there, and this attacker is going to try to subscribe to the vitals of the patient. Is going to try and steal that data, and it's also going to try and publish data through the motor control command to try and take control of the robotic arm that may be during a procedure, during some surgery that the surgeon is doing. It's going to try and tamper that data. So let me go ahead and I'm going to bring up here the applications. Let me see. I'm going to launch the applications. I'm going to bring them here to the background. Okay. We have here the orchestrator. We have the arm. We have the arm controller. I'm going to put it here at the bottom. And then we have the patient monitor. So we can see here the status of all of our applications. We have here the arm. Let me see. Second. Here we go. We have here the arm on the top right corner. You can see that the arm controller is sending some random commands for now. These are the angles of the different joints of the robotic arm. As you can see, this demo is super simple. And we have here the arm controller. I could stop it all, and then I could just play one of the joints just so that we can see a bit of movement there. But for now, let's imagine that the surgeon is controlling the arm and all the joints have different angles. And of course, we have here the patient monitor showing the vital signs of the patient. Now, we have here all these applications communicating with each other. And if I was to open Wireshark, important to notice that we are not using any sort of cybersecurity right now. If I open Wireshark, if you don't know what Wireshark is a traffic sniffer. You can, anybody is available online, anybody can use it. You can start receiving data or just seeing all the data that is coming through. And if I click on any of these topics, you can see here each of these rows is a packet in the system. And we have here also the names of those topics that we just saw in the diagram a second ago. If I click here on the vitals topic and I bring this window up here, this is showing us actually a lot of information, not just the topic name, of course, the IP address, the source, the destination, the different UDP ports, and all of that. But if I scroll down here to data, we can see how the vitals are also including not just the vitals of the patient. So somebody could come and take and steal this data, but also the name of the patient, something that is very critical and shouldn't be exposed just like that. So we can see already how Wireshark is able to see this data because it's sent in plain text. Now, we're going to simulate that an attacker comes in and is trying to take ownership of the system. So I'm going to launch this application that I have here for the attacker, and I'm going to go ahead and type a steal command. Let me make the font a bit bigger. Steal command. I click enter. As you can see, the attacker has been able to steal the patient's name, John Smith, and also some of the vitals of the patient. So this is just to show how simple it is to be able, in a system that doesn't use cybersecurity, to be able to steal some data. But not only that, but the attacker is also going to go ahead and try and tamper with the data. So if we look at here at the motor angles of the robotic arm, as you can imagine, any slight change to any of those angles during a live procedure can be really, really risky for the safety of the patient. Now, the surgeon is currently moving the arm around, but the attacker is going to go ahead and tamper with that data. Focus on the red line here. The attacker is going to go ahead and modify the angle at which the elbow of the robotic arm is currently at. So when I send the tamper command, sending tampering commands for elbow joint, you can see how it spikes up. Suddenly, the attacker was able to take control of the robotic arm. And if I just type it again, the elbow angle is going to go up again. You can see how dangerous this can be for a patient. And this is just to show the potential safety risks of not using cybersecurity in your system. Anything you guys, or Eric, wanted to comment here?
I mean, this is basically, right, because the data is in plain text and there's no security controls turned on, anyone can come in and just, get on the network, start basically intercepting the packets, collecting patient data, and then even be able to tamper with the controls of the device because, right, there's no authorization, there's no security checks in place. I guess the question is like, how does one, right, turn on those security checks?
Yeah, exactly. And that's what we're going to look into now. Let me go back to the presentation back here. That was the demo without security. Let's look at how we can do that exactly. We can use the RTI Connext security extensions that are going to help us protect the system, addressing the different controls that all mentioned earlier, basically the 5 pillars of cybersecurity, which are confidentiality, integrity, authenticity, access control, and availability, with a simple, very configurable quality of service that Connext provides. We can turn on all these settings. And thanks also to the SSL engine and a public key infrastructure, we're going to be able to protect the system and, of course, the safety of the patient. Let me focus a bit more on that public key infrastructure. This is what Connext secure system looks like with all the different components that are part of it. We have here P1 and P2 are basically 2 domain participants, that is 2 different applications in the system. And without cybersecurity in the picture, we would only have these 2 blue boxes, just the 2 participants of the communication communicating with each other. But now, to properly secure the system, we're going to need all these elements. We need a private key and also an identity certificate and a permissions file for each of the participants. You can see that P1 uses its own set of files and documents, and P2 uses a different set of files. Now, each of them uses the domain governance document, and all of this is properly signed by the identity certificate authority and the permission certificate authority. Now you can see how the more applications we add to the system, the more complex this is going to get. Your public key infrastructure is going, if you do this manually, is going to become harder and harder as the number of applications goes up. And that is exactly where Medcrypt's Guardian comes into the picture.
Yeah, so at a very high level, right, Fran was kind of showing you need to have unique keys and identities of each of those services. You need to be able to, do that at scale, right? Because those set of operations is not only for all your devices, it's really each device you have in the field needs a unique set of keys and certificates. So what we bring with the Guardian platform is the ability to have each device, each service have its own unique identity where keys are actually generated on the device. You can use we basically have profiles and policies where you can configure, right, what type of key algorithms you want to use, what key types you want to use, instead of having to update your source code, right, and do all that. All that stuff is configurable from our system, making it really easy to deploy and follow best practices. And all these keys that get generated for the device, for these services, all chain up to what we call a root of trust, where your root of trust is basically, right, your organization's certificate chain, and device certificates basically chain up to that, allowing someone or any system that's communicating to you or to any other interoperable systems to know that the device is owned by you, the device manufacturer. Eric, did you want to kind of dive a little bit more into the technical aspects of the platform?
Yeah, I'll try to go through this quickly. This is, what we're looking at here is a high-level diagram of all the different pieces of the Guardian platform, basically everything you need to establish proper security. And before we dig into the individual pieces, an important thread that we'll see in this demonstration is the establishment of trust among the components of the medical device. So even with cryptography turned on, with a library like OpenSSL, and data being encrypted, signed, and authenticated cryptographically, it doesn't mean the device is actually operating securely. And we'll see that in a little bit here. Proper trust is required to enable security that satisfies the FDA cybersecurity guidance for medical devices. So in this infrastructure here for the Guardian platform, in order to properly secure a device in this manner, we need to establish that trust of the cryptographic keys in the medical device, and the medical Guardian or the Medcrypt Guardian solution provides the necessary infrastructure and tooling to make it easy for engineers to establish that cryptographic security with the trusted keys in their medical device. So the Medcrypt Guardian solution covers the gaps that engineers typically encounter with other partial solutions. For instance, solutions from well-known certificate authorities, PKI vendors, cryptography library providers. There are a lot of pieces that are missing to do this end-to-end in an easy fashion. So out of the box, on the infrastructure here, for Guardian Cloud, we can see that Medcrypt provides private certificate authority backed by FIPS compliant HSMs, a PKI or public key infrastructure and key and certificate management, a device provisioning workflow system to centrally process CSRs and track and manage devices and their certificates. And then on the device side, right, there are two pieces to this. There's all the infrastructure you need to facilitate the trust, the root of trust, and all of the CSR processing. And then on the device side, you need some sort of cryptography library and you need to generate your keys and everything. So on the device side, we have a cryptography abstraction library called the Guardian Library. And that's used in the device to generate the correct key material, secure the keys on the device, generate CSRs and other device metadata to enable the device provisioning workflow to acquire certificates, manage key rotation and certificate renewal, and then provide a simple, stable API to deal with the cryptography operations to secure device data and communications. So the Medcrypt Guardian solution is a profile-driven cryptography abstraction. So engineers don't have to worry about setting up and maintaining all of this infrastructure or interfacing with crypto libraries, hardware, open SSL, wolf SSL, libsodium, HSMs, or crypto elements. That's all abstracted and handled by the Guardian ecosystem.
Thank you, Eric, for that explanation. So now we're going to combine these two products, right? We're going to combine Medcrypt's Guardian that is going to be able to provide all of the applications for Connect security participants to be able to protect our system. So let's go ahead and show the diagram for what this demo looks like with security in the picture. This is what we had before. We saw how the attacker very easily was able to steal and tamper with the data. So now we're going to turn on security, and security is going to allow us to stop this attacker from stealing or tampering with that data. Now, before we do that, before I launch the applications that are going to be using the Connect security plugins and or security extensions, and also Medcrypt's Guardian, let me show you what if you were developing this system on your own, you could be doing self-signing with OpenSSL. And Eric, would you like to make any comments on this?
Yeah. So again, as we can see with the script, self-signed certificates can be used to enable cryptography on the device. So what's the problem there, right? This cryptography is there. We're encrypting, we're signing, we're using keys. What's the problem here? Yes, crypto is active. However, the devices don't know if they can actually trust one another, with who's connecting to them and who's sending data. So the data is encrypted and authenticated cryptographically, but a bad actor can still connect and exfiltrate data or send bad data to the devices to make them misbehave. So again, this is about trust. We need proper trust of the cryptographic assets as provided by the Guardian platform. But obviously, a script like this will actually turn on the security.
That's right. So I'm going to go ahead, and because, Eric has explained the dangers or the potential safety risks of self-signing, I'm going to go ahead and launch Guardian so that it can sign and provision all of the applications with the right files. Eric, would you like to make any comments on what Guardian is doing here in the background?
Yeah, thank you. I think this diagram is good. So what we're looking at here is a high-level overview of what the process looks like to provision a medical device with proper security using the Medcrypt Guardian platform. The Guardian library will generate and secure the proper key material and CSRs based on a signed security profile. This is sort of the first step you're looking at here. Guardian will then send the CSRs and the device metadata via mutual TLS connection to the device provisioning workflow system, what we call the Guardian Cloud. Or the CSRs and the metadata can be uploaded manually or proxied in the case of an offline provisioning case, like some devices are not actually connected to the internet. They may be isolated at the hospital or on site. The CSRs will be verified and processed by the provisioning workflow system. And if approved, the device certificates will be signed by keys that are stored in FIPS compliant HSMs. Then those certificates, as well as the signed security configuration that drives the Guardian library, will be transferred back to the device. And then the device has all the assets it needs to enable cryptography with properly trusted keys. So Guardian drives this crypto ecosystem, and it gets it right. So medical device engineers don't have to be experts in cryptography, and they can focus on implementing clinical features in their devices.
Thanks, Eric. And we can see here, as part of my file system now that Guardian has provided, let's just check that it finished. Yes, Guardian finished doing all the steps that Eric mentioned for all the applications in the system. We can see here how we had the different files that make up the different documents that Connect security extensions need in order to enable that security. We have here, for example, a governance file, a permissions file, and we can see here how, for example, the permissions file for the ARM wasn't signed before, and after running Guardian, we can scroll up here, we can see that signed permissions file with the right signature. This was provided directly by Guardian, downloaded from the cloud. And also we can see as well the private key of the ARM and also the identity, the public key of the ARM. So now what we're going to do is to go ahead and we're going to launch again the applications. In this case, they're just going to be using security instead of not using security. So let me go ahead and do that here. There we go. I'm going to simply see. I'm going to pull them up here. We have the ARM. It is moving. We have the patient monitor, the orchestrator right there. And as you can see, the behavior of the applications is the exact same. We are still communicating. Things are working fine. There's no impact to any of the communication streams, or the behavior apparently is the same. So now what I'm going to show you is on Wireshark. Before, if you remember, I showed the vitals topic was sent in plain text, and therefore anybody could see it. This is what I was showing before. So I'm going to scroll down here on Wireshark. And as you can see here, we don't see the topic names anymore. Now, the only thing that we're seeing is a bunch of packets that just say secure body, secure postfix, and we don't really have any information about what that is. If I open now the same portion of the packet that I showed you earlier, we can see how we have a secure prefix, a secure postfix. This is the header and the footer of the encrypted content of the packet. And if I open up this secure body and the secure payload, now I just see a bunch of encrypted bytes, and I really can't tell whether this is for the vitals topic, this was for the ARM controller topic. I don't know what this is for, but most importantly, I cannot see the actual content. If this was to be the vitals topic, I cannot see the patient's name or see anything that's going on in the system. And this is very important. Now we have encryption. Now, based on this, I'm going to go ahead and launch the attacker, the exact same application that the attacker was using before. We're going to go ahead and launch it now. I'm going to open it up right here. Again, launching the attacker application. And I'm going to try now and steal the patient's data. Let's do that. Steal. There you go. And as you can see, after a few seconds, the attacker doesn't receive that data. And it is telling us here that it tried to steal data, but I didn't receive anything because no publishers matched. It wasn't able to match any of the publishers that were sending that data. Now, if I try to tamper, remember earlier, the red graph here went up. That was the elbow, one of the joints of the robotic arm, suddenly was moving because the attacker was telling it to do so. But if I try to tamper now, we can see how nothing happened. The attacker is now saying that it tried to publish several tampering commands. It actually did, but didn't go anywhere because the subscribers are not listening to the information that the attacker is sending. So we can see how the system is fully protected now. If I try to tamper again, nothing happens. Also, very importantly, we're not only protecting the system from this potential attack, but also the system, thanks to the Connext security extensions, and of course using cybersecurity now, all of the applications are able to send through the login topic, through the security login topic, a piece of information telling whoever is interested in, as part of this secure communication, that they actually denied the attacker from joining their communication. And this is actually printed in the orchestrator. We have decided to print it here. You can see how it says that the orchestrator, the ARM, the patient monitor, the ARM controller, and the patient sensor, they're all reporting the same thing. And that security topic actually says this domain participant, the orchestrator or the ARM, is reporting that an authenticated remote participant with this global unique identifier has been denied. So this is access control in action, because the attacker couldn't be authenticated by the rest of the applications. They're basically sending you a message saying, we have denied entry to the system to this domain participant, just in case anybody's interested. And this could be important in the future for the records of a potential cybersecurity attack. Would you like to mention anything here, Eric or Rom?
Yeah. So again, all of these devices, have cryptography and they can encrypt, sign, and authenticate data. Um, Really, the important piece here is that these are not self-signed certificates. These are not certificates generated in a way where we can't establish trust of the keys and certificates, because an attacker really could generate keys and certificates and use OpenSSL in conjunction with this whole solution, and it potentially still tamper and exfiltrate data because they can run cryptography too. The important thing is that we're establishing a trust boundary around the pieces of the device that should be communicating, and that really isolates the attacker. So without a solution where you're generating a proper root of trust and proper trust for the cryptographic assets with a solution like Guardian, you can still exfiltrate data even with cryptography active or tamper with the device.
Thank you, Eric. Now, would you like to go through the key takeaways of today's webinar?
Yeah, thanks, Ren, for that excellent demo, right? You're really able to kind of show that you can go from no security to a secured system that can scale in the market pretty quickly. In general, what we've seen when we talk about cybersecurity requirements from regulatory agencies like the FDA, we've seen an increase in regulatory threats, cyber threats over the past couple of years. We've seen the FDA enforce under the Patch Act that came out that got passed in 2023, multiple cybersecurity best practices like secure by design, having strong authentication and authorization controls, and making sure you have data integrity and your data is encrypted at both rest and in transit. What does this matter in terms of going to market? We've seen regulatory delays and a lot of business impact, and there's risk to patient safety. Per submission, we've seen about 15 deficiencies related to cybersecurity in the past year alone. And then that's quite high. And oftentimes it touches on things like self-signed certificates, not using the right key type, right, or insecure, outdated key algorithm. And these are just kind of different things you need to do to actually secure your system. So when we look at a joint solution, right, bringing Medcrypt's cryptography solution around device level security, where you can have each device have unique identities. You can do things like make sure you're having unique key generation on each device for each service to ensure data is encrypted and you have good authorization controls in place. And then using RTI's DDS secure extension to make sure you can ensure those complex requirements when it comes to the actual clinical device in terms of real-time data and communication constraints on performance are able to be met. In the end, with both of these solutions, you get those key things that regulatory agencies are looking for when it comes to protecting the data in transit and at rest. You're ensuring secure communication to not only subsystems within your system, but also external systems or cloud systems. And you're able to monitor, right, and manage the security activities throughout the life cycle of a medical device. Most medical devices, right, are not like general IoT devices. They're in the market for years, like 5 to 7 years on average, and oftentimes run into complexities in actually updating them. So by enabling these by improving the cybersecurity of the device and how data is transmitted and stored, as well as enabling things like secure updates, you're ensuring the lifecycle of device is able to stay on market longer. To summarize both the last webinar and today's webinar, we're really highlighting a more streamlined path to FDA compliance and other regulatory compliances. And in the end of the day, you're increasing patient safety because you're decreasing the risk and the risk to cyber threats by making sure your data is encrypted. You're protecting the sensitive data. You're ensuring system integrity when it comes to actual control of the system. You're improving patient safety, and that's really important in the medtech space. And as I mentioned a little bit earlier, by adding cybersecurity and these best practices around encryption and secure updates, you're actually improving the kind of the lifespan of the device and the ability for it to stay in market. because you have more secure ways of updating the device. You're able to be resilient, right? In terms of the kind of things changing in the future. Um, Oftentimes, right, especially today, we talk about things like crypto algorithms needing to be updated because of things like quantum, kind of quantum proofing, security algorithms, and those things, right, will likely change in the next couple of years. So by putting these security controls in place, you can be more resilient in updating your device in the future and making sure you're keeping the data secure. We do want to open it up to any Q&A questions that have come up.
Hey, would you like to go through the questions that the audience has asked?
Yes, everyone, if you have questions, please use the Q&A chat. Okay, I'll read one out. What have you seen from the FDA about using self-signed certificates?
Yeah, I can take that one. We have seen deficiencies around when it is apparent that a device manufacturer is using self-signed certificates, um and there's sometimes even using the same set of keys or certificates across a suite of medical devices. It ends up being a pretty high risk, because if one device is compromised, all your devices could be compromised. And it tends to kind of throw a red flag for regulatory agencies like the FDA, where they'll ask you more questions about what controls you have in place, and kind of understand why you're doing this, and kind of usually, it ends up causing more issues, right? And one of the biggest things is a medtech device, right, isn't developed in a couple of weeks or months. It's usually a long design and implementation process, and so it's really, really important to before you go submit to a regulatory agency, whether it's for a new device or for an update, to make sure you're not using self-signed certificates, or some other poor cybersecurity practices. And you do that early in your design cycle. And then, Fred, I think you've worked with a lot of medtech devices, and when they come knocking, right, and be like, "Hey, we're going to market in a couple of weeks. How do we turn on security?" Right? Can you kind of share some of those experiences and friction points you've seen? Oh, friend, you're muted. Just yeah.
Thanks, Sam. Yeah, I think that's something that you guys mentioned earlier was very important, right? Cybersecurity by design. By design is not a couple of weeks before going to production or submitting to the FDA. The FDA is definitely not going to like that. But even if that was the case, you need to have the proper measures in place. Cybersecurity is a company-wide thing. You cannot just, even though technically you can definitely use the cybersecurity, the Connect security extensions, and your own PKI, and that is going to, what we just saw here, this functionality is going to be the exact same, but you have a lot of exposure, right? That root of trust that you guys were mentioning, that is very important. How are you going to scale this? How are you going to mass produce your medical device? All of those things need to happen very thoughtfully beforehand, and you need to address all of that way before you're thinking of submitting to the FDA in the next weeks, in the next months, or even in the next year. Do we have more questions, Kate? We cannot hear you, Kate.
She did
Sorry
post.
about that.
Oh,
Oh,
I saw.
yeah, yeah.
Oh, I can go
Oh,
through it
yeah.
then, Kate. Thank you. I
Okay.
didn't see it.
Yes. Thank you.
Uh, yeah, there's a question here that says, what if the attacker was using the RTI security extensions? Would it be able to steal and tamper with the data? Well, that's a very good question. I actually, when I was learning about the Connect security extensions, early on in my career at RTI, I was used to playing around with Connext and, communication works and all of that, like we just saw in the first demo. But I started learning about the security extensions, and I'm like, okay, I'm self-signing this, I'm self-signing that. I just need to provision my applications, and I can just like, if I have all my system right here with all these provisions, all these documents signed by me, why couldn't the attacker also turn on the Connect security extensions and just use these same files or even create files of their own and just be able to join the system? Well, in the demo today, just for the sake of the demo, the attacker wasn't using the Connect security extensions, but even if he was, the important key here is that the attacker, thanks to Medcrypt's Guardian and that root of trust, it cannot get a hold of these certificates. But not only that, very importantly, it cannot get a hold of the certificate authority that is able to sign new permissions files, new governance files, new identities for that attacker application. And also something that I wanted to mention here is that in addition to the governance file that declares that the data needs to be encrypted or signed, or depending on what topic you want to uh, secure, you also have the permissions file that again is signed by the certificate authority, but these permissions files that are shared during the discovery process only allow you to publish or subscribe to certain topics, so that if at the biggest extent the attacker was able to get a hold of those, it can only publish and subscribe what it is allowed to. Would you like to mention anything here, Eric?
Yeah, yeah. I think this is an important point, right? Even with self-signed solutions that attempt to sort of do more of like a CA type implementation, you typically wind up with those CA keys, the keys that have to sign the device keys to establish the trust of them, not really secured properly, right? And if there's any risk of those being divulged, then your trust is out the window, your security is out the window. So a critical part of this is having, FIPS compliant HSMs with keys that are locked in the HSMs in an online platform that allows the devices to get their certificates properly signed by a key that's secured in that manner, through a pretty involved workflow for the approval of all of that stuff and the generation of all the data and the signing of all the data and the security configuration, returning that to the device. Everything's signed by those locked away keys in the HSM, so that you can rest assured that the trust is properly being transferred to all the keys in the device.
Thank you, Eric. Hey, do we have time for one more question? I see one in the chat.
Sorry, I was muted again. Yes.
Okay, perfect. This last question says, the demo looks great. Well, thank you. What's the complexity for my engineers to implement all of this? Maybe I can start with the Connect security extensions. These are the basic files that that the Connect security applications are going to need. You need one governance file for each of the domains. That basically declares whether you want to allow unauthenticated participants or not, whether you want to enable joint access control, whether you want to encrypt or sign the data, and then you need your permissions files, one for each of the applications that declares what topics your applications can publish or subscribe to. Now, as you can see, this is very straightforward. It's just a number of XML files. You just need to provide them to your applications through XML quality of service. Very importantly, you don't need to make any modifications to your applications, to the code of your applications. You don't need to do any sort of recompilation. You just need to link to the Connect security extensions libraries and provision your applications with the right files. And that is from the Connect security side. Of course, as I said, you need to provision those applications with the right files, and that's where Medcrypt's Guardian comes in.
And I guess to comment on what that means for medical device engineers, in terms of not only implementing the RTI Connext solution, but also the proper security behind it. There's all those pieces that we talked about earlier in the demonstration. Your infrastructure with the HSMs and the PKI and the provisioning workflow system. Controlling the crypto library on your device so that you can generate those unique keys, generate the CSRs, usually, more than just one of them, right? to transfer up into the provisioning workflow system to get your certificates back on the device so that it can operate securely. What the Guardian solution does is it gives your medical device engineers all of this stuff out of the box. They don't have to worry about setting up HSMs. They don't have to worry about setting up the infrastructure, the PKI, the provisioning workflow system. They don't have to worry about interfacing directly with a crypto library or a crypto element or hardware. All of that stuff is driven through a profile by the Guardian library, and it's going to do all that stuff for you. Secure and generate the keys, generate the CSRs, take care of the transfer to the workflow system, and then properly, using those keys and certificates in the device to establish this security. So it does save, a ton of time and effort and cost.
Thank you, Eric. Kate?
Okay, great. If there are no more questions, then thank you all for joining us today. Again, the recording will be sent out after this session. And if you have any other questions, don't hesitate to reach out to our speakers or email us at info@medcrypt.com and we will get your questions answered.
Thanks, everyone.
Thank
Thank
you.
you, everybody.
Thanks, guys. See ya.